Hi, everybody. So for today's 8-block day, we're going to be moving on to 7.4, and we're going to be talking about our first postulate to help us prove that triangles are similar. So just like when we proved that two triangles were congruent, we didn't necessarily have to go through and prove that all three sets of angles were congruent or that all three sets of sides were congruent. We were able to use some of our shortcut theorems and postulates like side, angle, things like that. So we're going to have some similar theorems and postulates for similarity. And the one we're going to talk about today is in 7.4, and this starts on page 254 in your textbook if you wanted to follow along. Page 254. So the theorem or the postulate we're going to talk about today is the AA similarity postulate or angle similarity postulate. And it says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So if you take a look at this diagram here, we would have, first of all, vertical angles in the middle there with angle BAE and angle DC or DBC. And then because you have parallel lines, you're also going to have alternate interior angles at at angle E and C, or at A and D if you prefer. It actually doesn't matter. But here we have at least two sets of congruent triangles in this picture. Therefore, we would be able to say that these two triangles are similar. So we could say that triangle ABE is similar to triangle DBC by the angle postulate. Angle similarity postulate. So really that's the only new concept we have, and we're just going to practice applying it a little bit. So example 1 says complete the following. So in this diagram here, we have two triangles. One is actually laying inside the other. We have this smaller triangle here, and then that is lying inside of this larger triangle here. So that's actually a diagram you see quite a bit. So I wanted to make sure we took a look at it in our notes first. So in this similarity statement, it's saying that triangle IKJ is similar to. So make sure when you're naming your similar triangle, you go with your corresponding angles here. Angle I would have to go with angle H. So we would say triangle H. And then since it goes from I to K, we would go from H to L. And then back up to J. And if you take a look, we would know that these two triangles are similar because first of all, they have a shared angle at angle J. And in addition to that, because of our parallel lines here, we would have corresponding angles at angle H and angle JIK. And we would have corresponding angles at angle L and angle I or JKI. So there's a few different ways we could show angle similarity with this diagram. Next part says find the scale factor of the small triangle to the large triangle. So remember, scale factor, you take your two sets or your set of corresponding sides and write their measures as a ratio. So first of all, we need two side lengths that we actually know. And so what you're going to want to do here is take a look at what matches up. Like 12 goes with X, we don't know that. 6 would have to go with this entire side length, which we don't know because we don't know Y. And then 9 would have to go with this entire side length, which would have to be 24. So we could do a ratio of 9 to 24, which would reduce to 3/8, or 3/8, or 3:8, however you want to write that. So we're going to use that scale factor to solve for our variables here. So first, let's solve for x. So x corresponds with 12. And since our scale factor, we went from the small triangle to the large triangle, I'm going to set up a ratio, or a proportion, I'm sorry, to solve this, where we do 12 to x equals 3 to 8. Apply your means extremes theorem. We're going to get 3x equals 96, and x would equal 32. All right, now let's solve for y. So y is over here. Now, y, actually is not an entire side of our triangle. However, we could still solve for it because we can write this entire side JH as y plus 6. So what we are going to do here is take our small side, which is 6, to our entire side length here, which would be y plus 6 equals, and then our scale factor of 3 to 8. And then we're again going to apply our means extremes theorem. And we're going to do, I'm just going to go ahead and do my distribution here. So that would give you 3y plus 18 equals 48. Subtract that over to get 30, and y would have to equal 10. And remember, if you're unsure, you can always plug that back in to double check, right? If you plug 10 in here, that would be 16. And just a quick double check, you could do 6 to 16 equals 3 to 8. First of all, 6 to 16 would reduce down to 3 to 8, or you can apply your means extremes theorem, cross multiply again, and you would get 48 equals 48, which is just a quick little way to verify that you have a true proportion there. All right, so we're going to take a quick look at two proofs now, because there's a couple of proofs in your homework. So for number 2, for problem number 2, I guess proof number 1, we are given that segment BN is parallel to segment LC, and we're going to prove that the measure of BN times the measure of LM is equal to the measure of LC times the measure of NM. Something I want you guys to notice is that this proof is our actual means extremes theorem. So it's going to be the proportional sides with the means extremes theorem applied to it. So what we're actually going to have to do is first prove that these two triangles are proportional, show their proportional sides, and then apply the means extremes theorem. So first, let's just start off with our given here. So we are given that segment BN is parallel to segment LC. That is given. Now the reason that's provided to us is because parallel lines are going to make congruent angles, and to prove that these two triangles are similar, we're going to need some congruent angles. So there's actually a few different ways to do this. You could simply use two pairs of alternate interior angles here with BC, or angle B and angle C, and then angle N and angle L. Or if you prefer, you can use your vertical angles 1 and 2 in the middle. It's completely up to you. I'm just going to use my alternate interior angles just because I can kind of do that in one step. But if you prefer to use one set of alternate interior angles and then one set of vertical angles, that's completely fine. So I'm going to say that angle B is congruent to angle C, and that angle N is congruent to angle L, and that is the alternate interior angle theorem. Then what we are going to do is, now we've shown that we have two sets of congruent angles. B is congruent to C, and N is congruent to L. Therefore, we can say the two triangles are similar. So triangle I can do that. MCL is similar to triangle MBN. Make sure when you name your similar triangles that you are putting your corresponding parts in the proper order. Okay, and then our reason for that would be the angle-angle similarity postulate, and that is a little similarity squiggle, not an N. My similarity squiggles sometimes look like weird little N's. All right, now that we know the two triangles are similar, then we know that their corresponding sides are in proportion according to our the definition of similar polygons. So what we can then say is that the ratio of BN to CL is equivalent to the ratio of NM to LM. And I'm picking those sides because those are the sides in my proof. And we can say that you can either simply write out that corresponding sides of similar triangles are proportional, or you could cite the definition of similar polygons or triangles. I guess definition of similar polygons is the technical term we used last time, but I'm not too particular about that. Then you can apply your means extremes theorem and say that the measure of Bn times the measure of Lm equals the measure of Cl times the measure of Mn, and that is the means extremes, property, not theorem. Means extremes property. Okay, so that's how one like that would work. Sorry, I just realized that for some reason I wrote a 7 instead of an L. Not sure why. There we go. Okay. So the second line should say angle B is congruent to C and angle N is congruent to L. All right. So now take a look at our last example here. This one kind of happens in two parts. This one, we are given that angle 1 is congruent to angle 2, and we're being both asked to prove that the two triangles are similar, which we'll do that using angle-angle similarity postulate, and to also prove that the sides are proportional, which we can do as soon as we've proved the triangles are similar. Since the proof is given in two parts, I just kind of split my columns here into two parts. So we're going to do part A and then part B technically. So for part A, let's put down our given. Angle 1 is congruent to angle 2. So we are given one set of congruent angles. Then all we really need is one other set of congruent angles, and we have enough for angle-angle similarity. And if you take a look, these two triangles are actually overlapping. They're asking us to prove that triangle JIG, that's this triangle, is similar to JZY, which is this triangle. So these two triangles are actually overlapping, which means they have a shared angle of J. So we can actually use the reflexive property there to say that J is congruent to itself. So we're going to say angle J is congruent to angle J. That is the reflexive property. And now we can say the two triangles are similar. Triangle JIG is similar to triangle JZY. Z, Y by the angle similarity postulate. Oh, and just a heads up, you will need to say angle similarity because next class we are going to be talking about some theorems that have the same names as like congruence. Like we're going to have side similarity. So if you just put SSS, then it's not clear whether it's side congruence or side similarity. So make sure you either write similarity or put the similarity symbol. Okay, once we've shown that they are similar, then what you can do is now show their sides are proportional. So technically this is like the second part of a continuing proof. So I'm just going to restate what we concluded in part A. So we concluded that triangle JIG is similar to triangle JZY. And I'll just cite part A here. Now we can say the parts are proportional. Measure of JG to the measure of JY equals the measure of JI to the measure of YZ. And we know that. And again, you can either say because corresponding sides of similar triangles are in proportion, or we can say definition of similar polygons. Either way with that. Okay, so hopefully that helps give you some ideas for working through your proofs and your homework. And as always, please just let me know if you guys have any questions. This technically isn't due until after break. However, if you have time to finish it, I think that would be great. So that way you don't have to work on it over break and maybe forget about it. And we should have some time tomorrow to go over homework questions. So I'm happy to take questions on this tomorrow. Well, tomorrow and Friday as well. So have a great day. Let me know if you need anything.